All right, folks, maybe we'll start back. I've got a quick presentation. Well, I'll try to make it quick, actually. First, I was told to do an hour presentation, and now we're down to less than half a minute. So what I'll do, so we can move on to the panel, is try to focus on high-level stuff and maybe just cut down a bit on the more technical slides and give you just a broad overview of what could be geothermal energy in the Canadian North. I'm actually doing research all across the Canadian North, from Yukon to Nunavik, helping different organization communities to see if they could develop geothermal energy. Believe geothermal energy is, well, energy from the earth that's need to be developed for people that live on the land. Obviously, our research has been conducted on the traditional territory of several First Nation organization. Here in Yukon, this include, for example, Kluani First Nation, in Northwest Territory, Dene First Nation, as well as also Métis First Nation, and we have also been working with Inuit in Nunavut and Nunavik. This picture just shows a pilot project that was implemented in Kuujjuaq. Kuujjuaq is the capital of Nunavik, where they install horizontal ground heat exchangers to heat the municipal pool that is under a greenhouse structure. So a fairly simple system that was implemented recently to try to reduce the amount of diesel use in the community. Actually, that's the goal, right, for these projects. Try to displace step by step some diesel. First, I believe we need to start with heating needs. Try to remove diesel furnaces and replace them maybe with some geothermal heat pumps, shallow system, and gradually move deeper and deeper towards system that could potentially produce electricity someday and replace some of these power plants in those remote communities. So the research I've been doing look at different type of system, the geothermal heat pump with shallow ground heat exchangers. So either install horizontally in trenches or in vertical well that have 100, 200 meter depth. That best work with in remote community with solar PV. Geothermal heat pump is an energy efficiency technology, and you need electricity for the system to work. And ideally clean electricity, so you could use solar PV to produce that electricity, run the heat pump, and make significant energy savings. According to our research, we believe this system can work in a near permafrost environment. In those closed loop, you have water and antifreeze, and the geothermal heat pump can operate down to a temperature of -7 degrees Celsius. And the idea is to cool down a cool medium, which is the earth, and transfer this heat with the heat pump refrigerant towards the building and heat this warm environment. Other system we've looked at is borehole thermal energy storage. So a bunch of small boreholes in which we try to, for example, take waste heat from a power plant and store it underground over a season and retrieve it in the winter when we need it, or store heat with solar panels. Those would require to increase the ground temperature, but could be a solution when there are long-term energy storage needs. And finally, the last type of system we've been looking at are the deep geothermal system with wells in, for example, in shield rock that could be quite deep, 3 to 5 kilometers, and could produce hot water to produce electricity. But this is kind of a long-term solution that could potentially be developed, but will probably not happen in the next 5 or 10 years, but maybe more than 10 years from now, when we'll need to reach our objective of being a carbon-free nation. Doing that research in remote community is really interesting because we look at very different geological environment, from the Cordillera here in Yukon, the Western Canadian Sedimentary Basin in Northwest Territory, and shield rocks in Nunavut and Nunavik. Most remote communities are in a subarctic setting. Very few are in a truly Arctic setting where permafrost is very thick. Most communities are in settings where well, the ground is cold, can be a little bit above 0 or near 0 degrees Celsius, and permafrost can be a few meters or tens of meter thick, which we believe is condition in which we can deal and install a geothermal system. Doing that research is really challenging because in the Canadian North, there's very little geoscience data. The Yukon Geological Survey have been doing a great job trying to collect that data where there are communities and there are people that live and that have heating needs. But what you see on that heat flow map of Canada is that in the Canadian North, I think there's more than 50% of the territory where there's no information on the Earth natural heat flow. So we have to think outside of the box, find creative way to assess potential from what we see from the surface geology, conduct some geological survey, and then justify drillings that will help to get better information on the subsurface. So this is what I've been done in Yukon. I think I can, well, basically go very rapidly over those slides as Mo already presented this. Some initial work, right, to find the sweet spot, the high spot, the red spot on the map where there could be higher geothermal gradient. Some boreholes were drilled to verify this, and some projects have been started. For example, the Burwash Landing project near beautiful Kluane Lake. Where actually our team have helped try to understand what's the regional groundwater flow, right? Glaciers melting on the top of these mountains, groundwater recharging and flowing toward Kluane Lake, and maybe some opportunity where there are fractures like or important fault like the Denali fault to intercept those fluid and eventually pumping up to surface and use it for space heating application. So the work we've been doing have involved like sampling the bedrock in this region to then conduct lab analysis. We've been doing also field test, inserting heating cable down the well to evaluate what are the thermal property, the geothermal gradient, and then the natural Earth heat flow to eventually provide information that would allow local community to develop these resources themselves. For a place like Burwash Landing, what could be envisioned, maybe a thermal pool with warm water tapped from wells. This is an example of Temple Garden Hotel and Spa in Saskatchewan. This is a place where they have hot pools, but fed by well water. It's a major touristic attraction for Saskatchewan, and similar pool complexes, for example, could be developed with geothermal resources if communities members are interested into this type of application. Other application could be greenhouse heating, aquaculture, district heating. There's various possibility with geothermal heat. Now let's move a bit out of Yukon, Northwest Territory, where actually the western part of the Northwest Territory is in the Western Canadian Sedimentary Basin. And actually over that region close to the Great Slave Lake, this is where we have the highest geothermal heat flow in Canada for the Western Canadian Sedimentary Basin, and different region with a very high geothermal potential for communities like Fort Liard, A River, Enterprise, Fort Providence, and Fort Simpson, and where some work have been initiated. Recently, we've worked more with the Eastern Decho region, for example, with Fort Providence, that is along the Mackenzie River, where we've been trying to evaluate what's the thickness of the sedimentary rock there, based on the old oil and gas well that were drilled. Fairly shallow sedimentary basin, less than 500,000 meter deep, and you have the basement underneath. Rocks involve a lot of shells that are not super permeable. So we've been trying to figure out what kind of geothermal system could be developed, as there's a very high geothermal gradient, but with low rock permeability. So what we've been doing for work is sample cores from the Geological Survey of Canada in Calgary, their core repository, to analyze the thermal property of the rocks in our lab. We've been also going on a boat around the Great Slave Lake to sample the basement that we don't see at surface, but that outcrops to the east of the lake, and also looking at the sedimentary cover to analyze those thermal property. That field work was done during the summer in August, where there were major wildfire in Northwest Territory. We actually had to evacuate and shorten our field season. But in our case, we were just doing work and had that was not a big deal to escape. And now our heart is more with community members that had to face those major fires, and I guess are still living some kind of crisis, right? Even though fires have gone down, there are still major logistic issues with people dealing with these wildfires. So basically, that field work that we do is well, to collect samples, analyze property in our lab, rock properties, thermal, hydraulic property with infrared scanner, gas porosimeter, or different type of apparatus, to try to envision what type of system could be developed. If we have like low porosity permeability rocks, then maybe there's a need to stimulate reservoir and increase the ground pressure to reopen fractures and circulate water. Those are enhanced geothermal system, the EGS, that are shown on the lower corner of my graph, and would be required for some of those rock type in the Northwest Territory in order to develop successful geothermal system. We've been also looking at the temperature data that are available in those old oil and gas wells. Those are our temperature data that were recorded when tests were being done in those wells, either flow tests, pressure tests, or geophysical well logs that give us some information on temperature, but temperature is not really at equilibrium, so we have to correct them and try to interpret to find what would be the mean geothermal gradient below some of these four communities that I'm showing there. There's some pretty high geothermal gradient, 40 to 50 degrees Celsius per kilometer. But as I said previously, the rock has low porosity permeability, so what we think could be developed there are maybe deep borehole heat exchangers tied with high temperature heat pump for space heating application. So the idea is to have like a 1 or 2 kilometer borehole with coaxial pipe inside, and you circulate the fluids come back up warmer, but the temperature, although that's deep and there's a high gradient, so the fluids circulate in the closed loop and the temperature is not that high, and you need the heat pump to lift that temperature and use it efficiently in a building for space heating. So that's it for Northwest Territory. Now I'm moving towards Nunavut, where there are more shield rocks and interest to develop geothermal energy in these 5 communities listed on my map. Very little data to work with, but basically shield rocks has a low potential. Sedimentary rocks showed in red may have a little bit higher potential. Right now, some work was done in Baker Lake, mostly by Kulik Energy Corporation and a consulting company called Respect, which actually work on the design of a borehole thermal energy storage system that could recover waste heat from a power plant, store it underground, and use it for heating purposes in the winter. A first borehole was drilled there. Temperature sensor were installed in the ground and core was recovered, and we're now in the process of analyzing the data. If a major underground heat store is being built, this would obviously melt some permafrost in the area. So what can we do to minimize permafrost thaw but maximize energy storage? That's a question that we've addressed in recent research. by developing different numerical model in which we simulate the operation of the ground heat exchangers, and we try different solution. Like we virtually try solution to see if we can minimize temperature changes in the upper layer of the ground that is sensitive to those temperature changes. So potential solution that were tried was to have ground heat exchangers that are not 100% filled with grout as we do typically, but we leave air gap in the borehole at the similar depth of the overburden. We've also looked at using a vacuum insulated tubing and thermosiphons that could keep the ground cold at surface, but allow us to store the energy on the ground. And what the graph shows is just the mean annual temperature of the ground at different depth for those different solutions. Solutions that could work best are the air insulation, vacuum insulated tubing, and thermosiphons that can potentially help minimize those permafrost issue while ensuring a safe storage for those systems. Now I'm moving to Nunavik, and I'll try to conclude after, so won't be too long. Nunavik is where we've done a fair amount of work with the community along the James Bay, Wet'magushtu, Kuujjuarapik, and Umiuyak, and also with Kuujjuaq, the capital of Nunavik, and Kangiqsualujaq. Their heat flux is fairly low, shield rocks. We would have to drill very deep to tap some hot fluid to do geothermal heating, but still we believe there can be some interesting solution depending on the size of the community. For a small size community, geothermal heat pumps for heating building would be the most interesting solution. And here, this is what we're investigating for actually a research station of the Centre Nordique du Québec, where here we're doing geophysical measurements to evaluate the thickness of the overburden, and then use that data to model the operation of a solar assist geothermal heat pump system. So in here, we're modeling two kinds of systems, where we just remove heat from the ground and use the PV panel to generate electricity and operate the heat pump compressor, and system in which we actually inject heat in the ground and use our borehole as a storage medium, which would be better for many buildings. That's the upper right corner of my graph. And the more solar panels we use, well, the more CO2 savings there is, since in that community, electricity is generated with a diesel power plant, and electricity is not that clean. So the more solar fraction you have, the more CO2 saving you end up. This is what is shown on my graph, like the smaller dots on when there is more solar panels compared to the bigger dots for which there are less CO2 savings. Other type of system we've looked at for the community of Kuujjuaq, capital of Nunavik, where there's about 2,500 people living, people that rely on a diesel power plant and diesel for space heating, is a deep enhanced geothermal system. There, since the geothermal gradient is low, on the order of 22 degrees Celsius per kilometer, so you have to drill very deep for temperature to increase. The system we envision would have 4-kilometer deep borehole, 2 borehole, one to pump, another to inject the fluid. Rocks are low permeability rocks, so they would have to be stimulated to reopen fracture and circulate the fluid inside the ground, and produce heat in that example to meet the space heating need of that community. So we had different scenarios, base case scenarios and best case scenario here are shown. 2 scenarios that can provide more energy than what the community needs, like the space heating demand in that community is about 37 gigawatt hour per year. While with the system, you could produce a bit more, and we think we could produce this economically with a levelized cost of energy that is in between 100 to 200, 250 dollars per megawatt hour. So this is a reasonable number, but it would only work if the whole community was linked to a district heating system and all the buildings would be heated together. If not, that would be difficult to implement because there would not be enough consumer to pay for such a expensive geothermal system with deep boreholes. Just to give you a summary, we've looked at different, technology through our research, which are the deep enhanced geothermal system, the borehole thermal energy storage, the BTES, and the ground source heat pump system that could be sometimes coupled with biomass, for example, to support peak loads, and the geothermal heat pump system to provide the base load to the buildings. And we did economic analysis and look at the levelized cost of energy of all these alternatives. That is, in my opinion, becoming more and more competitive. In red, it's the business as usual scenario. So heating with fuel oil that is around 20 cents per kilowatt hours. But those are in 2019 prices. Since then, the cost of oil have increased. And also recently, we've been looking at incorporating in our analysis the cost of oil spills. When oil spills occur in remote community, especially in Nunavut or Nunavik, they have to excavate the soils and ship the contaminated soils down south to treat the soil. So that's really expensive, and this can increase the true cost of oil heating in the north, such that geothermal technology are at the step that they are becoming competitive. And I think there should be some interesting opportunity in the future to replace the diesel system with geothermal, either geothermal heat pump or deep geothermal system, and provide some saving on space heating and reduction of CO2 emission and basically decrease diesel dependency. So to achieve this, I think now we're at some kind of turning point where demonstration project will be implemented in the future. Like right now, what I've shown to you is with most of our research project, we're collecting information on the ground and trying to prepare those demonstration projects that will happen with good knowledge transfer, development of drilling capacity, local drilling capacity. I think this is really important to achieve those projects. Geothermal is a technology that works very efficiently, but requires borehole to be installed in the ground. And this will, of course, occur if there is interest from local communities that want to develop their own resources. I believe that first, we must develop the shallow system, which are easier to implement and are a first step to show that geothermal can work in the north, and gradually collect information, show that it works, and go deeper and deeper to have more higher temperature system, and eventually produce more energy for both space heating and at some point for electricity generation. When looking at this, it is very important to consider not only the resource potential, but also the consumers, the people that lives in these communities. For a community that are really small, it could be very challenging to pay for the installation of those systems. So shallow system can work, or district heating system could be done at affordable cost, but electricity generation would be very difficult to justify if the population size is very small, let's say below 1,000 people. To conclude, just like to acknowledge various partners that have support our research, from private companies that give us access to their borehole and their core that is recovered at a significant price and is a great contribution for research, to government agency with who we partner to do research, especially the Yukon Geological Survey, that have been very keen in the last year. I've been spending time here in Whitehorse for a research sabbatical, and they've provided me an office, and I had a lot of fun being here this whole winter, more or less. Also, First Nation organization that give us access to their land, to governmental agency that obviously fund our research. That would not be possible without motivated students that spend some time in the communities, look at geological conditions, and come back with some very interesting solutions for a greener future. Thank you.